All right, so let's try this again. Let me know if this camera right here is too close to my face. Up there, it was like I was always looking down. So, chapter 7. This quantum theory and the electronic structure of atoms. Such a breakthrough in physics and chemistry. This was a very exciting time. So, to make it short, up until this point, so the 18th century, the end of the 18th century, basically all of Newtonian physics was well known. You could calculate the trajectory of a cannonball and other stuff, and it was used to explain most things, most phenomena in the world. And in fact, Planck, it's also called Planck, this guy at the top, that's an A. Let's see if I can draw that. When he wanted to get his doctorate in physics, his advisor said, "There's nothing left to discover in physics." And, well, he showed his advisor something else. And what happened is there were a couple of natural phenomena that could not be explained by classical physics. And so a new physics had to be invented. And that also included some math. Or they took math that was already present in other areas and then combined it to make quantum theory, which is arguably the most empirically successful theory mankind has ever come up with, and it's responsible for all sorts of things: electronics, lasers, GPS. Well, that also has to do with relativity, but everything hugely successful. So we're going to give you a brief overview of some of the characters involved, and then we're going to go over some of the main topics of it. And ultimately, we're going to go deeper into the electronic structure of atoms, which, as far as those are concerned, the orbitals of the atoms are derived directly from the Schrodinger equation. So this is my second go round. Hopefully I can make this shorter than the other one, and hopefully my audio is working right now. All right, so to start, just a quick background. Planck, 1900, he came up with the Planck constant, which you've seen. Is that, let me get my white going. So quantized. And you'll see that in a bunch of other equations. So that was an important development because previously everything was considered to be continuous. So from 0 to 1, there's an infinite amount of numbers between 0 and 1. Well, in the quantum realm, there are discrete energy levels. And hopefully you'll see later how that's important. But that's the foundation of quantum theory. Einstein, this is not for his theory of relativity. It was for his work with the photoelectric effect. So what he found there was that it wasn't the intensity of light that would allow for, say, metals hooked up in this apparatus to create a electric current, but it had to do with the frequency of light. Bohr came up with atomic theory that was built upon. De Broglie, he more or less said that everything with mass, if it's anything with mass, if it's moving, also has an associated wavelength. And there's a very simple equation that you can use to calculate that. So Pauli was important as well. I forget exactly what he did, but it was it was more of a mathematical formulation of some stuff. And then Heisenberg uncertainty principle, You cannot know the exact momentum and position of, say, an electron at the same time. You can know more of one or the other. And Schrodinger, of course, who devised the what we call the Schrodinger equation. It's this beautiful wave mechanics equation that can be used to pretty much describe any kind of phenomena. Born, he was important, the Born-Oppenheimer approximation, at least for stuff that I do. And then Dirac, this is mainly mathematical. He merged, or basically got some agreement between quantum mechanics and relativity. Anyway, we're going to go basically right with the McGraw-Hill lecture, and I might gloss over some stuff. But so to start with, quantum mechanics relies heavily on calculating things, the math behind waves. And so just briefly here, we have property waves. You have a wavelength, and that's the distance between either the crest and the next crest, or the trough and the next trough. So that's inversely proportional to its frequency. The amplitude has to do with how high the wave is. And so, as I already mentioned, frequency, it's the number of waves that pass through a particular point per second. So this is a generic representation of a wave. So here, speed nu, or no, that's not nu yet, u is equal to the wavelength times nu. I know that's a little confusing. So nu is the frequency. And so I'm just going to use my, come on. Why isn't this going? All right, there we go. I got a mouse and a pen. So light as a wave. So instead of the previous one, it used u as the speed. We have here c for light. Light in a vacuum, speed is constant. It's about 3.00 times 10 to the 8th meters per second. It changes a little bit depending on what medium it is in, so it is slower in anything that has mass, and there's a complicated reason for that. But for our purposes, it is just 3 times 10 to the 8th meters per second. So, with this simple equation, what we can do, c is constant, we can rearrange either the wavelength or the frequency nu, and say solve for the frequency or the wavelength on the other side. And from this, you can calculate either of these. So, in these kinds of problems, you're going to be given one of the variables, and you're supposed to find the other. So, you can simply rearrange the original equation into these two. So, I think we have an example right here. So, in this example, we have a photon with wavelength of 522 nanometers. What is the frequency of this radiation? So 522 nanometers, that's 10 to the minus 9th. We have to convert it into meters so that we can put it into our equation, and it will agree with what we have as far as the value for C. So rearranging equation 7.1, replacing U with C, speed of light, gives us this relationship right here, which I drew backwards up here. It's the same thing. So with these kinds of problems, they're not very hard. Be sure, do not forget to convert to account for the wavelength being in nanometers, so convert it to meters, multiply it by the speed of light, and then you get this right here. So this is what we converted on the previous page. It's underneath the speed of light, and then we get our frequency, which is in hertz. When you do these problems, you don't have to, double. It wouldn't hurt to double check, but on a test, if you're being timed, instead of redoing the problem, just make sure that the answer is reasonable. When we're dealing with light frequencies where's my mouse? It's over here. In this range, 10 to the 14th, is reasonable. And as we'll see in a little bit, the electromagnetic spectrum actually varies a great deal. So here we are, sort of an artist's representation of the electromagnetic spectrum. On one side we have gamma rays. They're very damaging, basically burn off your skin. X-rays can be cancer inducing. You can see from here, everybody should be familiar with X-rays, is that they're able to penetrate soft tissues. And the white here, bone that's more dense, they're not as good at penetrating those. So the frequency is very high for this area right here in the electromagnetic spectrum. And as we progress this way, the wavelength increases, the energy of each photon goes down. Ultraviolet, sun produces the entire spectrum, but ultraviolet is the one. Ultraviolet A, ultraviolet B are the ones you hear about that we wear sunscreen for. These have to do with when it hits matter, it creates an electronic transition, and that's basically what results in color. The visible spectrum that we see is tiny, and this has actually been expanded, I think, if the scale is quantitative. So in the visible region, it's a tiny little slit, and color is through evolution. This is how we see the electromagnetic spectrum, or a very small chunk of it. Beyond that, we have infrared, microwave, and then radio waves. So just a side note, ultraviolet, as I said, is electronic transitions. Visible, also some electronic transitions. Infrared has to do with vibrations, heat. Microwave has to do with rotations. And radio waves, unless you guys end up taking organic, not as important, but it has to do with nuclear spin of atoms. So, moving along. One of the problems that I was talking about earlier that classical physics could not explain was the black body problem. So heated solids, when they're heated, you can think of early incandescent light bulbs, and some still have this, but they have a filament of tungsten. They run a current through it, and it gets very hot, and so it glows. It's a very inefficient source of light, generates a lot of heat. But anyway, they could not explain the intensity and the wavelengths generated by heated metals. So when solids are heated, they emit electromagnetic radiation over a wide range of wavelengths. Radiant energy emitted by an object at a certain temperature depends on its wavelength. Well, they couldn't come up with a mathematical formula to predict this. Here's another simple equation related to light. So E equals h nu. Planck's constant, and this is how he discovered it, is addressing the black body problem. It's a tiny number. It's joule seconds. This, combined with another equation, basically was able to predict the emission of radiant bodies, heated bodies. Another big problem that was solved, this is by Einstein in 1905, was the photoelectric effect. So what they had is you have, dozens of different metals, and in this experiment, it's absolutely amazing in its simplicity, but illustrates the point very, very well. So what we have is we have this metal right here, and you can see it's supposed to be a half curve, but really it's surrounding the entire cathode in the middle, if I'm saying that right. I think the anode is negative and the cathode is positive. But so we have a voltage source and a some sort of meter that detects stuff. So the incident light, and I drew this over here. Actually, the slide is probably better. So when we hit the metal with light, they tried all sorts of different things. They would change the frequency, the intensity of the light, which just means the sheer amount of photons that are hitting it, and it didn't behave as they had originally expected. They thought more intensity would generate a greater, flow of electrons, and that is true, but it has to be, the frequency of light has to be above a certain threshold. So what Einstein devised was took that E equals h nu previously from Planck and set this, so E would be over here, and he just substituted h nu for E is equal to the kinetic energy of the electron plus some work function of the metal. The work function differs depending on what metal is being used. So rearranging this, you get kinetic energy on one side, h nu on the other, and we just subtracted the work function on the other to the other side. So one of these problems is quite straightforward. Calculate the energy in joules of a photon with a wavelength of this. So we're not actually going to do the photoelectric yet. We're just going to get comfortable with calculating the energy of photons. So if this is the wavelength, it's in nanometers, infrared region, relatively weakly energetic photon. And then this one is much more energetic. The solution is similar. We take both, convert the nanometers into meters, and plug it into our new light equation. So energy here is equal to h times the speed of light over the wavelength. So here we have Planck's constant, speed of light divided by the wavelength. And then we get joules, and that's a tiny number, but we're just talking about one photon right now. So again, is this answer reasonable? You guys have no reference for it, probably like how much energy is in a photon. So for now, yes, it's reasonable, but we can compare our answer from A to B. So if we go back and look at A, it's infrared region, longer wavelength, lower energy than say the X-ray region. All right, so doing the same thing that we did in A, we see that the amount of energy in a photon in the X-ray region is hundreds of thousands of times greater than that in the infrared. And I'm getting that, I'm ignoring this, but 10 to the minus 15th versus 10 to the minus 21. So that's 10 to the 6, more energetic. So always see if they're reasonable. All right, in this example, slightly more complicated. The work function of cesium metal is 3.42 times 10 to the minus 19 joules. Calculate the minimum frequency of light required to release electrons from the metal. Just got really dark. I think we have a storm coming. Calculate the kinetic energy of the ejected electron if light of frequency 1.00 times 10 to the 15th inverse seconds is used for irradiating the metal. So let me turn this back on. There it is. All right, this should, oh, there it goes. too many controls. Alright, so let's go down and show what the strategy is and then actually do it. So the relationship between the work function and of an element, metal, and the frequency of light is given from the above equation. So that is, let's write that out. So we have two representations of it. H nu is equal to KE plus the work function. I know I already mentioned this, but I'll say it again. The work function is specific to the metal. So we have that. It's tough when I have a stylus and a mouse. They're competing for the cursor. Okay. Hopefully I didn't go too far. I didn't go far enough. Alright, now I'm in the right spot. So we'll say, I always draw a line. The work function, you can put abbreviation for what metal it is. It's 3.42 times, microphone is in the way, times 10 minus 19 joules. Alright, so this is for A. So we already have our strategy, and they lay it out right here. H nu is equal to the work function. You rearrange, here's a constant. This one, the work function was given. So we can just plug in the work function that we have here, 3.42 times 10 to the 19th. Keep your units. I will forget sometimes, but it will help you in the end. If you cancel all your units and you get something else, different units than what you're looking for in the answer, then you can usually trace back and see what you did wrong. So in this case, I have my calculator out, but I will trust the notes. 5.16 times 10 to the 14th inverse seconds. So that's how many cycles per second for says here. I don't think I'm going to do every single problem in these notes, but it'll be good to see a couple of them. So in B, rearranging the previous equation, we get kinetic energy is equal to H nu minus the work function. Thusly, KE is equal to H nu minus W, which is, after we plug in the different numbers, we get this value right here. So I think you guys are all pretty sharp and shouldn't have a problem with that. On a quiz or a test, the most difficult part would be just conjuring up these equations. Really, you just have to do one, and then you can rearrange it into the other. Alright, maybe I'll take a break there, make sure my audio is still working, and then come back and do the next section.